In the LAMMPS website, you could see that we have different sections. This part is about the downloads and also the free repositories. This part is about documentation. This is the online manual of the LAMMPS. Of course, when you of course, here. Okay. So this is the online version of the manual that it is easier to work with. Today I'm going to work on this manual, but when you install the software, there is also a folder that all the PDFs of documents are there, including the manual. And here is a section about the results. Here is the publications that have used LAMMPS software. You could also see the two papers that I already discussed with you yesterday. It is the bending characteristics of carbon nanotubes, and this is the torsional characteristics, and it's actually an honor for us that it's indexed here. These are the pictures. There are different pictures that people, for the papers that are already done with LAMMPS. And for example, here you could go to the relevant literature, and you can find some information about how to perform the simulation. There are no scripts here, just the overall idea of the work. But in this page or here on the movies, okay, there are more examples. And here are the movies that are created through the examples of the LAMMPS itself. So, for example, here, this is something that is already done by LAMMPS. And here you could see the input scripts of it. And okay, these are the support. These are some books about the MD simulation. And these are, as I told you, some workshops that the LAMMPS developers themselves have prepared. And I think this one, the virtual LAMMPS workshop, is one of the best because it is already held in virtual. So this is the first day, it's for beginners, and also it's introduced Ovito. It's really good software for visualization. Okay, so this is the website of LAMMPS. But what does LAMMPS mean? It is the acronym for Large Scale Atomic Molecular Massively Parallel Simulator. Okay, and it can simulate a broad range of materials. For example, in the solid state, it can simulate metals, metal oxides, semiconductors, and also biomolecules, polymers. And it is mainly used to simulate materials with atomistic scale. But the fact is that it can be used for the coarse grain and mesoscale, and also at the continuum scale. For example, let me show you here that if you're familiar, of course, we have a peridynamic expert here, but peridynamic is also a meshless continuum model that is used for high deformation problems. It is used for crack or for impact. And it is one of the things that can also be done in LAMMPS. So it is not just limited to the simulation of atomic scales, as I talked to you earlier. We can do mesoscale also in LAMMPS, and also some problems in continuum mechanics can be simulated through LAMMPS. Okay, and as I told you, it can be run on one processor, or it can run parallelly. Okay, after you install the software, go to the folder that it is already installed. Done. If you don't know where it is installed, you can click on the install executable, and it again asks you, do you want to reinstall it? You can say yes, but don't reinstall it. Just take the address that it's installed already. And also online participants. Could you find a folder? Okay. Great. Okay. Okay, in this folder, you could also see some information. You could see the doc folder. It is the documentation, different documentation. It is the LAMMPS manual. It is a really complete manual, because as I told you first that it was released. That was the only thing that people could use when working with LAMMPS software. It is actually the same as the online version, but we are going today to work on the online version. And this is the folder, the example folders. There are about 72 items, 72 examples that can be run on the LAMMPS. And the lowercase, they are usually just have one a script to run, but the upper cases, they include some other examples. So it's even more than 72 examples. And it's better if you want to run a simulation to start from a simple script that is relevant to yours, and then improve it little by little, and then make it more complex. These are the potentials that are used in the LAMMPS software. It is, for example, for the silver, it is the EAM potential that we talk, that it is used usually for metals, or for example, AI Rebo, it is for carbon. And also here are different executables that are used. Since we have installed the serial software, you can see this executable. It has different, for example, this one, MSI to LMP. It is the one that you use when you are making an initial configuration in Materials Studio, and then you want to import it from Materials Studio too, because Materials Studio is a really convenient software to create, for example, polymers, biomolecules, and then with this executable and of course some other commands, you import it into the LAMMPS software. Okay, now please go to the example and click on this. We can copy it somewhere else to work on it. Okay, you do not have these two folders files right now, but there are actually three basic documents or files that we have and we need for performing simulation. The first one is the input script. Usually it's in dot something. And when you do the simulation, we have two other types of files. One is the log file. It writes everything that is done during the simulation. And what is the other one is the dump file, that it saves the coordinates of the atoms so that further you can use it for making the videos or pictures. Okay. Now here, this is the main script that we're going to work with. Okay. The main script of the LAMMPS is constituted of 4 main parts. Okay, the first one is initialization, in which, for example, you define the very primary settings for the script, that is units. It's about the dimensions. And the second one is the system definition. For example, you define what is your atomic structure, you define what is your initial configuration, any initial settings on the geometry is actually done here. And the third one is simulation settings that, for example, define the parameters that you want to be computed during the simulation. And the last one is run simulation. Actually, we have 2 main commands for doing the simulation. One of them is run. It is the one that uses the time integration that we talked about it previous days. Where is the time integration? Yes, one of them is this part, the time integration, and the other one is actually minimization. The minimize command is usually used before you do the simulation to just relax the structure and avoid any high energy interactions. Okay. Just a little about the parsing rules. Okay, if you have this symbol, an and symbol at the end of a line, it means that you should continue to the other line. And every, of course, language has something as a symbol to show the comments. And for LAMMPS, this is the number symbol. Yes, we call it number symbol. Hashtag symbol. Number sign. Okay. For example, yes, as it's written, this is a comment. You can also write a comment at the end of the line. And this, when you see the $sign, it means that it is a variable. If it's just a 1-letter variable, you can simply write it like this. But if it's a sum, it has some other letters, we usually put it in curly brackets. And another thing about LAMMPS, which is a bit important, yes.
This example for
which one?
The variable which was more than 1 letter.
You put it here. You know, like this, my temp. Okay. And yes, another important thing is that LAMMPS doesn't read the whole script all at once. It just goes line by line. So, for example, here, this sequence of commands are different than this sequence of commands, because here it sets the time step 1.5, and then it runs for 100 times, then again it runs for another 100 times. But this, it goes with 100 times with the default time step, which is usually 1, and then here it changes the time step, and the second run is with this time step. Okay. And in the LAMMPS, usually when we have a command, in any command, for example, this one, the first one is the command, and the other ones are the arguments of the command. Okay. So let's start. This is the script that we have for the crack simulation. I don't know. Yes. Please open the Index crack file. Of course, I'm just going to explain to you. Or maybe it's better to first run the simulation, and then we will talk about the scripts to see that. Okay, we should open the CMD window in this folder. Okay, there are some ways to do it. One is to open the CMD from the run command and then say cd, and the other is to press the shift button and write, okay, for me, it brings PowerShell window here. Then I should write CMD if I'm not wrong. No. Didn't come here. Now this interface is actually CMD. Or another easier way is that just click on the address bar, write CMD, write enter. Okay. Now, you could also check from the bin folder, but for me, this is the LMP underline serial.exe -in I, and then put the tab bar, the tab keyboard to bring in .crack.lmp. Okay.
The list of files in the current one. The list of the files.
Yes, it brings the list of the files. So for me, the simulation is done. For you, is it done?
For us, it's not just needed to type LMP. LMP dash E.
Yeah, I know. I just wanted to say that you haven't done it. This one was LMP serial. Okay, that's because actually in my own in the bin it was named as LMP underline serial, but maybe in your folders it is just lmp.exe. See,
It's not
type exe. Okay, so you probably, if you have installed the version I have write to you, you can also write this -in I, press tab, and then do this. For me, it doesn't work this. Okay. Okay, is it working for you? The online participants?
no. Okay, so I don't have to write all the line.
Okay, can you write the code to run it? Yes, of course. But I would like one of the participants, okay, to share. Okay, Francesco, could you please share your screen so I can tell it to everyone? Okay, this is the code, but oh, you have done it, yes? Oh, so you can done it. Okay. What about others? Oh, it's great. Okay, if anyone has tried but he's not successful, just tell me, because it's better if I show on your system. Okay. Okay, of course, please note that this is an extraordinary case, that the simulation runs this fast because it's so simple and oh yes. Okay. So after it is after we run the simulation, you could see that we have the log files, and it's produces everything that is run during the simulation. If you open the script, we have some lines with hashtag the dump files, the dump line at line 67. It has made a comment, but dump is a command that is used for outputting, so that you can use it for having the videos. Just delete the comments with the command lines that starts with dump or dump modify. Also this one, because it is in continue of the previous command, because we have an and symbol here. Done? Done? Okay. Now, please run it another time.
Number sign before the comments start with dump.
See, the number signs and also the lines that are after the dump with the and symbol. Did you do it? Could you see the pictures? Yeah. There should generate some pictures and also a video.
No, just numbers and in the folder.
No, in the folder.
Okay. Yeah. Okay. Oh.
Okay, this is the video that you have already made. Now the online participants must talk. Could you follow? Francesco? Okay, perfect.
Yes, that's supposed to.
Okay. Oh, what has happened? Professor?
Yes, it's okay.
Okay, yes, I'm waiting for also the present participant to do it. Okay. Now let's see how we have done this. Well, as I told you, it has different, the script has different, maybe we can, is it working? Okay. Okay, I want to, let's put it where. I want to explain the script. Okay. Okay. So as I told you, it has different parts. The first part is about the initialization of the system, in which we do the overall settings for the system. The first command is dimension. Okay, whenever you want to use the command, it is really recommended to use the manual, because you know it's a very good software, but anyway, it's open source and it's not commercial. So sometimes a very small change may cause not working of the program. So for example, for this dimension, you could usually just simply put it here, and we use the dimension command. As I told you, the first one is the command and the other ones are the arguments. Here we just have one argument, that it can be 2 or 3. Okay, it shows that the overall dimension of your work, that it can be 3D dimension or it can be 2 dimension. We have for every command we have a description here. Then also we have some restriction. For example, some commands cannot come after or before some other commands. For example, the restriction here is that this command must be used before the simulation box is defined. So it is the very primary lines of the command that we signify what is the dimension of the system. And here it also shows the default value. So the default value is 3. If you don't write anything, it will run as a 3-dimension program. And the second one is the boundary of the system. We have some words here. Again, let's go and see how we should define the boundaries. Okay. In the boundary command, the arguments, we can have 3 arguments. It can be P, it can be F, M, or N. If it's P, it's the periodic boundary condition that we already discussed the first day. This is the periodic boundary condition that we say that we have made open the bounds of the system. It can be F, which means that the boundary is fixed. Okay, so they cannot pass the boundary here. It can be S, which means that the boundary is not periodic anymore and it is shrink wrapped. What the shrink wrap means that the boundary changes until it encompasses all the atoms. So it moves with the farthest atom in the system. Okay, it moves with the atoms just to embrace all the atoms. But here, when we have M, it is non-periodic and it also moves, it's shrink wrap, but with a minimum value. So for example, the volume of the system cannot be lower than a special value. And if it's, yes?
Is it changes?
Yes, we usually, we should define a simulation box. Anyway, we should define a simulation box and we should define the boundaries. And but we
use the S, for example, or the M. The box is still rectangular, or
yes.
Okay, so it didn't change, for example, spherical or something like that.
No. We okay, for the online participants, one of the participants asked that is the size of the box changed when we the size of the box is usually rectangular, and so if you, for example, have a spherical shape, it is inside the box. Of course, we use the rectangular shape because it's the easier one to write, but any shape that can be replicated so that it just covers all the domain, it can also be a box. For example, we also have not spherical box, but we have some box with, for example, six faces, so that they can put beside each other, and it always doesn't need to be, for example, just perpendicular. It can also have angle, but it should, it should be able to cover all the space.
And one more question. Also, we can use other, coordinate system like a spherical.
Yes, we can use polar coordinates, but the simplest one is the rectangular one. And even sometimes we use a periodic, but we do not mean really a periodic. We consider it so big Okay, and for example, the system is in the middle of it, so it doesn't interact with other atoms in other boxes, but it is literally isolated. And if sometimes, here you can see that we have two letters. If you have two letters, it means that one side, for example, is fixed and the other side is shrink wrapped. If you have two letters here. So what do we have here? We have the boundary condition, the first one, and in the X direction, in the Y direction, we have the shrink wrap. And in the third direction, in the Z direction, it is periodic. Just pay attention, because we have the dimension, 2D dimension here, the third one should be periodic. We don't have any other choice. So if you write anything else here, you will get an error. And okay, the third command is atom style. And here you see that it is atomic here. The atom style shows the building blocks of the script. It is atomic, or for example, it can be molecular. You can have different arguments here. There are very, very different arguments. It can be atomic, it can be molecular, it can be spherical, especially when you are performing coarse grain here. When you're performing coarse grain simulation, it is not atomic anymore. The building block is different. It can be molecular, for example. And this is neighbor. We're defining the neighbor. Again, if you remember, here we define the member, and the thickness of the neighbor is defined here. Okay, but we have here 0.3. What is this 0.3? Is it angstrom? Is it nanometer? Yes, it is the thickness of the layer, as I explained. This is the thickness, the skin here. But we don't know if it's, for example, angstrom, it's nanometer. The fact is that we should write something here like units. But as we haven't written, it is using the default version of it. Okay, let's see what units is. Okay, like anytime when you want to perform a simulation or you want to solve a problem, you have to know in which unit you are working. Okay, it can have, for example, the metal unit, the LJ unit. Once you specify the units, you specify in which units all the parameters are calculated and what is the meaning of all of the quantities. For example, in the real unit, if you use a mass, it is in grams per mole. It is implied that it is in grams per mole. Or for example, the velocity is angstrom per femtosecond. If it's, what is the sound? If it's metal, again, for example, the distance is angstrom. If you don't specify anything, what is the unit? The default is LJ, and actually it's dimensionless unit. Okay. You could see here everything has become dimensionless. So actually we don't need to write this because it's a default value. Okay, and this is something, sometimes you have a command and you have another command, and usually it's, for example, this modify, or that it should precede another. It alone maybe doesn't have any meaning. You should first say that you want to have a neighbor list, and then you want to modify the first comment. It is the type of the neighbor list that you are facing, but it is usually this one. You could also check if the other parameters. And the neighbor modify, it's delay 5. It means that you don't rebuild the neighbor list earlier than 5 time step. Okay, so this is the initial part of the script. Every script has its own initial part, and then we want to create a geometry in the script. There are 2 ways to define the geometry. One is to use the LAMMPS itself, which is simpler, but sometimes you read the geometry from an outer source that we are going to check both here. The lattice structures that we explained here are already defined in LAMMPS, so we can use this. And you know that we have different lattice structures. We have FCC, we have BCC. Okay, so here you define the type of the lattice structure, but pay attention. Every time you want to use a command, use the manual. I do not go into manual again, just not to bore you, but okay, this is the lattice command. And this shows the type of the lattice. It can be BCC here, FCC, and here is the lattice number. Okay, it is related to the structure. And then we should define a region, okay, in which we want to put our atoms in which we want to build the lattices. Of course, you know, this is the language of the LAMMPS. Maybe we could use something else, but it prefers to first define a region in it. So we define a region. This is the name of the region. Let's also see this command in the manual. So this is the name of the region. It is ID. So it is the user assigned name for this. Nothing, just you say something. This is the name of mine. And then we have a style. It can be block. It can be cone. It can be cylinder. Here you can define many different ellipsoid, prism, sphere. Okay. And there are different arguments for it. For example, for the block one, this show the lower limit. The second one show the higher limit for the X direction. This is for the Y direction, and this is for the Z direction. Okay. So we define a region from 0 to 100, from 0 to 14, and this is the thickness that we are considering. But this one is not really important because we are periodic in the Z direction. And then after we define the region, we told it to create a simulation box in this region. Okay, as I told you, it is the language of LAMMPS. To build a simulation box in this region, this is also a name we assign to it. It's not really important. And we say that, I think we need to go here. This is the number of atom types that you want to put in the simulation box. This is the region ID, and there are some other keywords. Okay, so this is the region ID that we have previously defined. And then create atoms. It just, you know, build the simulation box, and here we put atoms in the simulation box from one type of atom, the first type of atom that we have. Okay, and then we define the masses of the system, each type of the atom. You know, here we just used one, but here we have 5 types of atoms. Actually, you know, they have the same mass, and then you will see that they have the same interaction energies. We just use it to have different colors here. But you can have different types of atoms, but here we just use it for different colors. Then you should define the mass of the atoms, and then so the initial geometry is created, and then we should define the interaction energies. Okay, the peristyle here is LJ cuts. LJ means that the peristyle that we are using is Lennard-Jones. Okay, and cut means that it is Lennard-Jones, and we have defined a cutoff radius for it. And the next parameter is the radius of the cutoff circle. After peristyle, we should usually say that what are the per coefficients? Do you remember, for example, here we have K, we have sigma. Here, for example, this is the Lennard-Jones form of van der Waals. We have a sigma here, we have an epsilon here. Okay, these parameters differ from atom to atom. So we should define what are these parameters. And here in this work, we just have the van der Waals force. So these are the only two parameters that we should define, and also the cutoff radius. But for example, if we are using a system that it has, these forms, we should also define all of these parameters for it. KL, K theta, we should define all these parameters. So here we just have the Lennard-Jones. We should define these two parameters. I will talk about these two stars. This first one is the epsilon, and the second one is sigma, and this one is the cutoff radius. Okay, it is the same as here because we have just one type of atom and we want to use the same, but sometimes you can define between this atom and that atom uses, for example, a larger cutoff radius, because you know that in the Lennard-Jones potential, it has further effects also. When you can here use the numbers 1, 2. It means that between the atom type of 1 and atom type of 2, use these parameters. Between the atom, for example, here, between the atom type of 2 and 2, use some different parameters. Okay, but when you just put a star here, it means that between every types of 2 atoms, you can use it. Okay, so this was the initial. Then we want to define the groups. You could see here we have different colors and they are different groups. Okay, we have a group here that are fixed. We have a blue group here that they move upwards. We have 2 groups here that there is a crack between them, and a simple group here that forms the other parts of the system. So 1, 2, 3, 4, 5. We have to define 5 groups. For this, again, first we define a region. We show what is the region of the group, and then we assign a group number to it. Okay. The first region, we provided with the block, so it is rectangular, and these are the bonds of the block. Okay, when you write inf, it means from minus or positive infinity. Okay, so it means that if this block is from minus infinity to positive infinity in the x direction.
Because we have a limited box, so the minus infinity for this is the boundary.
This is the first region. Yes. Yes. Here, this one, when we have minus infinity to positive infinity, we want to define this yellow region. What was your question?
Because we have a limited box.
Yes.
For the lamps, minus infinity is.
Yes. Yes, it's the left bound of the box. The question was that why do we use a minus infinity to positive infinity? That's because, we don't want to find, for example, what is the first of the box, what is the last of the box, and to be sure that all the atoms in this region are included. We use minus infinity and positive infinity. But the fact is that it started from the very early of the box and the upper edge of the box in this direction. And the next one is a minus infinity to 1.25. You can see in the y direction. And in the z direction, we use minus infinity to positive infinity because it's periodic and we want through all of the simulation box to have this region. Then this is the name, we define the group. This is the name of the group that we are assigning ourselves, lower, because it's lower. And we say, because there are different methods to define a group. Sometimes you define it through a region, and we have also other types. It is not used here, but there are other types. For example, from the type of the atoms, you can define the groups. And okay, here, so we define a group here. Then we have the second region. This one. Minus infinity, positive infinity. This is the limit on the y direction, and again on the z direction. Which one is this one? The upper blue one. Okay. And again, okay, we have the upper region. Then we define, this is another use of the group function, group command. Then we define the boundary. We say to make them union, to make them one. the lower and the upper region, and call them boundary. This is the name we assign to it, okay? It's not important. This is the boundary, the lower and upper are the same. Not that they are the same and now we have no lower or upper, but we also call it the boundary. Okay, because we want, you will see that we want to perform them in a different ensemble, so we put them in a different category. And then the mobile region, it subtracts all from the boundary. It is another use of the, let me show you here, just see. Well, the group command is one of the commands that have a lot of styles. And for example, if I want to use the subtract, the arguments is 2 or more group IDs. So we should define the group IDs. You have also here, for example, group, boundary, subtract. You should define the first one that you want to subtract other from it. It's all, and then there are the groups that are going to be subtracted from it. No, we are not still making the crack here. This is the mobile. There are the bonds that are moving. There are the atoms that are moving. We subtract all from the boundary. So we are creating this whole region. The red one, the green one, and the blue. Yes, we are fixing you haven't fixed it actually yet. We have just defined, this is just defining the configuration. Then we set a different type to it, okay? We just set different type, as I told you here, just because of the color. We say want to use the group command, and the left upper that we have already described, we want it to be of type 2. And okay, just assign different type for different groups that we have already defined. Now we want to apply initial velocities to them. Okay, this is actually an unnecessary command here, but we are defining this is a compute. Okay, this is a very frequent command that you use to define a large variety of quantities. This is the compute command. The first one is the name of the compute that you assign. The second is the group that you want to perform the calculations on it. And this is the style of the compute and any arguments that it wants. For example, here compute 1 all 10 means that the name of the compute is 1. I want to perform the computation on all the atoms. And this is what you wanted to calculate, which is the temperature. But you can, for example, put any equation here, not just temperature. So here it calculates the temperature, and here we define a velocity. For the mobile, creates 1.0, and I will explain to it. We define a velocity for the upper set, and we define a velocity for the lower. We just exclude it, yes. Let's see what is. Okay. The create one, the velocity, the group ID, the style. If the style is create, we have the temperature value, and we have a positive integer value. It's just a number, a random number, any random number you can create. Okay. So it uses the it uses this algorithm to build the initial velocities. So the temperature here is 1.01. Sorry, 0.01. And here we then we put a fixed velocity to the upper region. It is 0.3 to the y direction. Okay, and what is the unit of 0.3? Yes, it's dimensionless. But for example, if it was metal, it's dimensionless right now. But if it was metal, for example, it was angstrom per picosecond. If it was metal, of course, now it's dimensions. And then this one, you know, it gives a ramp velocity for the mobile case. You know, it says that it has the velocity in the y direction. It starts from 0, it goes to the 0.3, but in a ramp direction. So it linearly just maps a velocity to all the atoms in this case. Okay, now we have the fix command. It is also an important command. Actually, anything that we want to do, we should do it within the fix command. And it has a lot of styles and a lot of arguments. Okay, if you remember, we talked about different ensembles that we have. One with the fixed total energy, one with fixed temperature, and one with fixed temperature and pressure. This is one of the things, but not limited to, that is defined in the fix command. If we want to sometimes move a number of atoms besides the velocity command, we can use the fix command. If you want to sometimes do an averaging between some variables, you use the fix command. As so many, you could see that so many things are defined under this command. But here we are using it to define the ensemble. Okay, fix one ensemble, one is again the name, all shows that on what parts of the atom we want to do the fix command, which is all here. And this is the NVE ensemble that we already talked about it. And this one, fix 2, is again the name, boundary. This is why we defined boundary. To set forth null, 0, 0. We define this because, you know, we already, for example, have defined a velocity for the upper command. So we do not want to do any further time integration on it, so that we don't want to change the velocity. Okay. That is actually why we set the force here in the X and Y direction to 0, and in the Z direction, okay, when we put it null, it means that we do not want to change the number, just put whatever you find from the integrations. Okay, actually all we wanted from the settings and the compute is finished, and here we just want to do the simulation and also set the output parameters. Here we define the time step. It is 0.003. Again, it's dimensionless here, but it can be, for example, if it's another unit, for example, real, it can be picosecond, femtosecond, or the thermal. Maybe it's not obvious from its name, but shows, you know, with the thermal command, you define what are the outputs that you want from the script. When it is 200, it means that every 200 gives me these outputs. And it just wants the temperature. Okay, in the thermal modifier, you can say that what do you want from the script as an output. Here it's just the temperature, but in the other we will you know, get a lot of other information from it in the next example. And here is when we define the crack. The interested participant in the crack, here is where we define the crack. Okay, in the neighbor modifier, you know, there are some ways. For example, you can define some atoms and remove it. This is one way to define the crack. But it is a simpler way. Neighbor modify exclude. It is the arguments type 2 and 3. It means when you are building the neighbor, do not pay attention to type 2 and 3, so they do not come to the neighbor list, so their potentials are not calculated. So there is literally nothing between them. Okay, so this is one of the ways actually to define the crack between these two. So we don't delete any atoms. We just say that there is no potential between them. And then the dump are the just, you know, a way to extract and make files that are we restore information in it. These are the names, and these are again the group of the atoms. It can be all, it can be boundary, it can be mobile. And there are different arguments here. You can extract here it extracts the atoms, the atom IDs, and also the coordinates, this one. You can drag images from it, and also you can make movie. Okay, but up to this point, no simulation has happened. You know, it's just settings. This is the time that you will do the simulation. When you see the run command, it starts, okay, it reads everything, but it puts all of these fixes. It starts from the first fix and do all the things that you have written here. Okay, so this is the part that it's actually repeating. It is repeating these parts. And it says that it should be simulated for 5,000 time steps. Okay. So we have finished this script. Now what I want you to do is
but where we have defined the time steps?
The time step, you know, it has a default. Yes, it has a default value. For example, for this time, real, we have femtosecond. Time is in femtosecond, okay? So if you write 1, it means 1 femtosecond. But for example, because, you know, I told you in molecular dynamics, the time step is usually 1 femtosecond. But if you use the metal and you still want a femtosecond, you should, the time here is in picosecond. So you have to write like this, command like this. For example, here, time step. Because 1 femtosecond is 10 to the power of -15 and the other, so you should define it. Okay, if we perform it, as I told you, we have a log file. These are what we asked it to produce during the... No, we didn't ask it, just do the coordinates. And also, this is the dump file that it shows the coordinates of the atoms during the simulation. The first one is just the ID. As I told you in molecular dynamics, we have an ID for each of the atoms because each of them are determined for us. And this shows the type of the atoms. You know, here it was just for the color, but we can have, for example, the carbon atom has a different atom type, the hydrogen atom has a different atom type. And then it is, we had, okay, this is 4, this is 3. As you remember, this is 1. We have a lot of 1 because we had a lot of mobile region, also 5. And these are the coordinates. Okay. Now, what I want you to do is that in this image, the crack is on this side. Okay, I want you to change the position of the crack to the middle. And I want you to change the atoms from this one that is just to a metallic one. I want to change the type of the atoms. As a hint for the metallic type, you can also use the examples. We have an example here, the shear one. Yes, here we have the peristyle. EAM, as I told you, is for metallic, and for example, it has used nickel here. Between all the atoms, use this file that we already, okay, it should just write these or something. because it potentials, you could see that we already have, in the first versions, you should also copy paste in the folder, but now it runs it automatically. Okay. 10 minutes is fine. 5 minutes.
What's the first?
The first, I wanted two things. One, to change the position of the crack. After we did this, just perform your simulation, we will check. And then we want to change the type of the atoms. Put the crack from here to here. It can be the same as the one here. Also, the online participants, you will be called and asked to share your screen.
For example, this minus this point and this.
It says, for this, you just, need, because, okay, we have defined, here, we have defined the region, okay? So we have to change something here.
Yeah, but I should I design another block or can I just
Move them.
no, but if I for example no, okay. I'm not finding the red one.
No, the fact is that, we just first define everything
Okay.
for the create atoms.
So the red one is
Yes, it's everything other, because you could see that we create the atoms with the red one, which is the one. Okay, then we assigned other things to the other parts. So the default is that all of them are red. Then we
should
yes, we override the type to some other parts. For this step, we just need to change the position of the crack, and for the next step, we will change the type of the material. The command to execute the scripts. Okay, I will write it. This is the command to I'm talking to my participant. This is the command for running the script. Okay, as a hint, you just need to, here is where we define the other types. So you just need to change probably these parts. At the first step, just change the position of the card. But if you have done, okay, proceed. Oh, sorry. I mean, you should change these parts. Left upper, left lower. You should change the dimension of these parts. Yes, the length of the rectangle, you could see here, 0 to 100, it is in the x direction. From 0 to 40, yes. The length of the crack is, here, 20, from infinity to 20. So this is the length. From the log, how do I get the images? Okay. Marco Contatori, from the log, how do I get images and movies? No, we're not getting images and movies from the log, okay? The initial version of the crack. In the initial version of the crack that we have from the example folder, okay, you could see that these parts are with a number sign, okay, and they are made comments. The dump command is actually the command that gives you the images or movies. Of course, this one, no, this one just gives you the, okay, coordinate. So the only thing that you need to do is to just, delete these number signs.
Yeah. Just to change the values in these two origin comments.
Could you do? Okay. Leonard. Have you done it?
Yeah.
Oh. Did you? Okay. And you also get the images. Okay. Okay, anyone in the online present has done the exercise? Anyone? Okay, almost everyone in the presence has done it. Come on. Okay, I would have you doing? Okay. Okay, I will ask Dr. Oniero to. Could you share your screen? Oh, of course, of course, of course. I should activate it from here.
What do you want to do?
I want to activate.
Maybe I activate mine other than increase.
Okay. No, I will mute this one. Okay, but
No, because first you want to share your screen, your audio will not be shared. Your audio will not be shared until.
Yes, but for some reason it's created only the images and not the. Oh, it's okay. It's you know, this is the parts related to the movie. Yes, this is the part related to the movie, and you have to maybe, you know, I don't know, this one, you know, you do not have your video player doesn't support this one. Maybe maybe this is this. Just here. Okay. Okay. Marco, have you forgotten to have you put also remove these lines, these number signs? Okay, okay. I activated them. Okay. So maybe I can too. Okay. So Marco, could you please share us your screen? I should pause share so that he can share. No. Yes, yes, I remember. Thank you. And could you bring us your yes. Oh yes, you have. Yes, you have removed them. Okay, but okay, the crack files LAMMPS. Perfect. Of course, it is not exactly in the middle, but it's perfect. Oh, so you have the video. You're not seeing?
No, it is chat. The video is in front.
Oh, sorry. Sorry. Could you please show us again, because the video chat was in front of others. Could you please show your image again? Your movie. No, it just won't showing the images and sequence. Oh, it's okay. Okay, it's okay. Perfect. Okay, it's perfect. And also, could you please show us your script and what you have changed in your and what you have changed? Perfect, thank you. What you have changed in your script? Yes, yes, here. Of course, it's not exactly in the, of course, thank you so much. Thank you.
Should be 40.
Yes, thank you so much, Marco. Great. Thank you. Okay. Yes, yes. Thank you so much, Marco. You could stop your screen sharing now.
And if you want to change the metal,
Yeah.
how it should be.
How would it should be? You're going to figure it out. Oh, it's okay. Thank you. Thank you so much. Okay, thanks to Marco. Actually, the present participant has also done it. We should change here. You know, this is the line that we should change because it shows the left upper and left lower regions. And the only thing that we should do is to change the x directions, the x values of these regions. It is from -infinity to 20. And actually, this one is also from -infinity. The length of the plate is 100. Okay, so the middle is 50. Okay, the length of the crack is 20. So we start from 35,
40.
40, sorry. 40 to 60. Sorry. Oh, yes, yes. I'm their engineer. Okay. Of course, I changed the one in the, like this one was in my own folder. Yes, yeah, I should change this from 40 to 60 again, from 40 to 60. Now let's run again. Okay, now you could see that the position of the crack has changed. Okay, well, now let's make it a little harder. Here, as I told you, we are using the Lennard-Jones potentials, okay? And they are actually not representing any special kind of material, but just one to show you something. But now I want you to change the material from this to the metal, okay? So we should change the interaction energy, also, for example, the masses, yes? And maybe the units, because for metals, maybe we need to have a different unit. It is still atomic, no, it's still atomic. And I, okay, suggest you to use this in these examples. Here, the shear, in that shear, it has used, you know, the first and okay. It's already put to it, okay? Okay, could you please do it? Because you may encounter some error you want to deal with.
Do you encounter errors?
Yes, yes. Try to counter error. So I again repeat, now we want to change the material types to metal. So we need to change the mass of the atoms. We need to change the potential of the atoms. And maybe some other things like units. and boundaries, maybe. You should change?
The region
No. No, no.
from this shear file.
No, please do not use the shear file. I just want you to, do not use other things in here. Just use the potential. Okay.
The lattice parts.
The lattice part. Yes, it's for something else, Just, here we have the lattice.
It was this.
Which potential? Use the exact potential here. Use the exact, what are the lines related to potential? Yeah, EAM. Because, for metals, we usually use EAM. So maybe just need to.
The classic for what is the old
No, sorry, let me go.
The simple one. Because I want to yeah.
Oh, yes. And open the shear corner. In the example folder. The shear.
So, clarifications even more. There's nothing to complain about. Sorry, but unless there is no sheer part.
Certainly.
Mass of
Nickel.
nickel molecules.
Yes, nickel atoms.
Because the former example was dimension.
Yes, it was dimension.
Here we should.
Yes, you should assign something.
So we just into all the groups.
Is any of the online participants have questions? It's okay if you do not know what to do. You can just share your screen and I will explain to you on your screen. I was talking to online participants. No, online participants. Oh, you're talking to us. Oh. Marco Conciatori. I liked one file. Which file? You mean the in.shear one? The in.shear one, if maybe you're talking about this because the files have not changed here. This comes from okay. This one, and actually EAM is the potential that are used for metals, okay, and for different metals, okay, we have different potentials. Please just go to the potentials. Okay, and the input file, of course, sometimes it automatically can get it, but if it's not, just go to the, again, I will say, to the LAMMPS folder that you have already installed, go to the potentials, and then find this file. This is what you're searching for, okay? Just copy and put it in the folder that you are already simulating. Okay. In 1 minute, we are. Could you do?
Also here, we should define neighbor means couple.
Yes, you do not need to change anything. Yes. In EAM, it also has, EAM is a potential. It's not as simple as Lennard-Jones, just doesn't have two potentials. If you open this file, you could see that it has many different parameters because it's actually a many body potentials. Every atom is affected with a lot of atoms around it. So it's not as easy as Lennard potentials, but no, we define cutoff radius for everything to just control the computational cost. So what does it want? What does it say? This time is incompatible with the simulation.
Like this is fine. You change it to true.
Yes.
Here.
Yes.
Which is the
Wow. Yes. So if you change the dimension, also like this.
also.
Units. The units is metal, the dimension is.
Oh, dimensions for the count always agree.
Yes, but and this is the mass.
I thought this.
Yes, for metal and for this one, for instance.
No, I will check. I will check it.
No, it's okay. For the mass, it's okay.
Does that just
The atomic number of
rate of decline is fine?
Okay. There's so many neighbor beings. So many neighbor beings. Have you changed the neighbor beings?
Neighbor.
No, I don't think it is needed.
We should change the neighbor also.
No. This is the problem of Markov. I don't know why have you. Because you just need to. This is the base, Marco. This is the base script you're working on. So try to change this one. And I don't think there is any need to, change this. Okay. Okay, let's work this one together. What we need here is to. Okay. And I want to tell you that it's quite common that you change something and you receive some errors. Quite common. So we want to use metal material here. I use peristyle EAM and the per coefficient I want to, the metal I want to be nickel. It can be any other thing. So you will, from the EAM, from here, you can use, any other metal that are available here. And if not, maybe you can find it from elsewhere and you can put it. Okay, so I'm going to use this one here. This one is on the examples. This is the Lennard-Jones potential. This is where we have defined our interactions. I just delete these ones and put these ones here. Okay. And then we have as I told you, we have Lennard-Jones, but for metals, we should use, okay, or you should receive the error. Let's receive the error first. And then, okay, and also the mass, here the mass was 1, but we should put the mass of nickel here. What is the atomic mass of nickel? Atomic. This one? So let's run and see what is happening. Okay, it doesn't go because the EAM potential file requires metal units, but LJ units are in use. Of course, we didn't say it's LJ units, but we didn't change the default version. So here we say it should be metal. Let's see if it's okay now. Yeah, I want to. Okay. This is the error that he received. It's maybe because he hasn't changed the dimensions. Okay. So for the, I haven't changed. He hasn't changed also this one. Okay. For the nickel, okay, we have a different lattice. The nickel is actually the FCC. Okay, with this lattice dimension. So we have to replace this one. In these PowerPoints, we have also, I think we have nickel here. You could see that. Well, nickel is FCC, okay? If you use BCC, I think I have the version that I used BCC and it was just, exploded and couldn't kept the atoms near each other. Okay, so
the crystal does not match the energy.
yes, the crystal actually, yes. Okay, so let's run it again and say that the lattice style is incompatible with simulation dimension. Okay, so for this lattice style, which is FCC, we should use the 2D dimension doesn't work, so we should use the 3D dimension. And let's see what happens now. Before that, let's just also increase the dimension here because this is too low. Maybe this one is better. Of course, it increases the simulation, but not so much.
What is the direction of the box?
This is the direction, yeah. Because it want to produce this lattice, it's better. So, Marco, you should change what was the very last change? The very last change was that, we changed the lattice, the first version, it wasn't FCC, okay? But when we use the nickel, the compatible lattice structure is FCC for it, okay? I use this one, the lattice FCC 3.52, and I put it here in front of the lattice because this one is compatible. And the very, very last change was to change the dimension from 2 to 3, because for this type of lattice, we need a 3-dimensional piece.
Also
Maybe, yes, I also changed the region, the amount of the thickness to 2. It was so small, so we changed it. And that, okay, and that you see that it's running a little. After this one is finished, we are going to have a little break. Do you want a break? Okay. Okay, for 10 minutes, and then we will come back. And I will show you another example on tensile deformation of carbon nanotubes. You could see that. Yeah, it has changed. Updating thing. Okay, it's finished. These pictures are not as beautiful as it should be. I'm going to talk about VMD and we're going to work a little bit with it, but just right now, we just want to show a better version of this one. Okay. This is what the metallic parts look like. You see that, you know, the types of failure is a bit different from the other one. That was something like the fracture, so you could see the cracks here, but here, you know, you mostly see the, okay, it's ductile, and you mostly see the, of course, the slippage of, you know, the crystals on each other. Instead of breaking and fracture. And also, you know, the shape of the crack are a bit different.
Crack is controlled.
Yeah, because this is what was really happening. In reality, for example, the crack is really critical for brittle materials because it starts and, you know, it goes on. But for ductile materials, no, sometimes, you know, a crack is started, we have some yielding around it and it's off. So even the stress concentration factor, if you're familiar with that, the stress concentration factor, when we have a abrupt change in the geometry, okay? This is important when we have a ductile, we have a brittle material, not a ductile one like metal. Okay, so we are going to have a break. See. Okay, for the next work, we are going to simulate the tensile deformation on a carbon nanotubes. Okay, you can use the data, the two files that I sent you last night. Have you received it? Okay, could you please bring them? I wanted to do this one together again, like the previous example, but I think that we will not find enough time. Okay. In the CNT and CNT the data. Okay. As I mentioned previously, there are two types of defining the configuration in the LAMMPS. One of them is to define it directly in the script. That is what we did in the crack case. But the other type is that you can read it from an external data file. For example, for CNTs, this is the case. Sometimes, you know, for the configurations that are too complex, you cannot define it in the LAMMPS software because it's not really a suitable software for making the structures. It's better for just doing the simulation, time integrations, and so on. So In this example, we're going to perform tensile tests on a carbon nanotube. First, here we also define the boundary conditions, and we also define the units. Okay. For the why do I use the metal unit here? It's not metal carbon, but I'm going to use a Tersov potential. Okay, and for the Tersov potential, we need to define it as the metal. Okay? It's just some inner restrictions in the LAMMPS stuff. We also define the atom style as atomic, and then we go to create the geometry. Here we use the read data command, and then we bring the name of the file. Okay, we bring the name of the file, and we should also put the file in the folder that we want to do the simulation. Oh, zoom in. Okay, sure. It's better. Yes. Okay. Thank you for your recommendation. Okay, so here we use the read data command and we say the name of the file. Here we again define the potential. This is the AR rebel, is the potential that we are using. This is the cutoff radius. But again, you have to, for every command, please just refer to the manual, because this is not 3 angstrom or anything. It is 3 sigma that is that we defined here. Here. Okay, so it may have any other variation. Okay, and here we also have the pair coefficients that we again want to use this file, like the one we had for the metals. We also have another file here. I will show you in the potentials. Okay, this one. Let's also copy to our folder to be on the safe side. And okay, so we enter until now we have entered our configuration. We will talk about how to make this configuration. We have defined our potential, and now we want to do the simulation setting. It is quite similar to what we did in the crack. Okay, but here we again define the upper region. Something for, sorry, the lower region, -infinity to 3. It's the lower region of the tube. And also we define the upper region. We define something at the middle atoms, which is subtracted from all of the atoms, minus the lower region and upper region. Okay, I think before proceeding, it's better to make the initial structure of carbon nanotubes to know what do we mean by the upper region, lower region, or something. As I told you previously, there are different softwares that you can produce nanotubes with it. Okay, VMD, nanotube builder, and a lot of other softwares. Today we want to use the VMD software. Okay. And just a single thing about nanotubes. As I told you, we can hypothetically think that nanotube is not real, but we can think that nanotube is formed from a graphene sheet that it's rolled. Okay, and based on the line that we are rolling this graphene sheet, we have different kinds of nanotubes. It can be armature, it can be zigzag, and it can be chiral. You could see that, for example, in the armchair, it's something like a chair here, or you have to think that something like a chair, and this is the zigzag types, okay? And this is the chiral. We are going to produce these with VMD software, the second software that I sent the link. Okay, VMD is, when you open it, we have 3 windows here. This is the command window. You could write directly here some commands. This is the window that it has different tabs, and okay, you can work with it to import the structure or do some other things. And this is the graphical window. So here I want to use it. We usually use this to visualize our results, but we can also use it to create some configurations. For example, here I want to create carbon nanotubes. I go to the extension. Which one do you think? Modeling. nanotube builder. Okay, it has two different configurations, both graphene sheets and also nanotubes can be built here. Okay, and as I told you, you know the different configurations of CNC. We can have two letters for it. Okay, this is on the paper. We usually use two letters to show what is the line that the nanotube, the graphene is rolled around it, and it is shown by two index. The two index are the same for armchair, and for zigzag, one of them is 0. Okay, so I'm going to simulate a 5 armchair nanotube with 3 nanometer length. Generate nanotube. The nanotube is built. Okay. You can change the display here. I really like the orthotropic one, not the perspective one. Oh, you want to do it? Okay. Okay. Let's do it together. Let's do it together. The orthotropic ones a little bit. Okay. Done. We go to the extension, modeling, nanotube builder. And then it brings here in this part, the generates nanotubes. You put 5, which means that it's armchair. And you put 3 here. For example, if it was, it can be 6, 6, you know, if these two indexes are the same, it means that it's armchair. It can be anything. And if this one is 0, it means that it is zigzag. Let's also build this one to see. Okay. This one should be the first one. This is a very small zigzag. For the zigzag, it should be a little bigger to have the same diameter. Okay. You can see zigzag shape. Okay, so this is the nanotube. Could you build it? And for example, you can change, you know, the representation. It's not needed. Why, if you want, you can do it. It can be CPK, so it's ball and stick. It can be this one. Of course, it's better to decrease the size. Usually, this one gives a better figure. Okay. And then we just need to save the coordinates of this nanotube. Here we come here, save the coordinates. And here you could define which is the file type. Because, you know, in different softwares, you need different format. PDB is a really a famous one, but we use the LAMMPS string one. Or we can also use the XYZ, it just gives the coordinates, but the LAMMPS one is more comfortable for LAMMPS.
Sorry, where was the name?
We right click on this, right click on the name, save coordinates, LAMMPS string, actual LAMMPS trajectory. Yes, to save value, and then the save button. Okay, the online participants. Am I mute? No. The online participants, could you do it? Come on, it's VMD, it's quite simple. Marco? Marco Concettori? Okay. Then you save the coordinates in the folder that you want to do the simulation. Okay. Okay. So I named it as CNT underline VMD. This is the folder that it has created. This is the file that it has created. It is quite appropriate for LAMMPS, but it is not quite what we should import in the LAMMPS script. This one that I sent you last night, this is the type and the format that it's more appropriate, that is actually needed to be imported in the LAMMPS. Okay. In this data file, the first two lines, no, we don't need to write anything. It is just considered as a comment if you're writing it. Is it okay? Are you following me? That's it. Okay. Then we need to say again zoom. Okay. It doesn't go further.
No, because for the online.
Oh yes, of course. Thank you. Okay. And then here we should say how many atoms we have. This is then we should say how many types of atom we are going to have. But again put it 5 here. We do not have any other type of atoms. It's just carbon. I just put 5 here for the color. And then you have to define the size of the simulation box. And then we have defined the masses, but you know, you have to, it's really better to use a file that is already, you have done something with it. For example, it's better to use, for example, this file that I have sent you and import if you want to run any other simulation, because a single line, unfortunately, or sometimes a single word, extra word here just ruins it cannot, you know, proceed it. And here we have the atoms. The first one is the atom ID. The second one is the type. And the others are the coordinates, okay? This is the one that is appropriate for LAMMPS. And this is the one that we have just get from VMD. So we just make some simple changes. LAMMPS data. This is not needed, but whatever. And this is the atoms. This is the same here. Then we should say the atom types. Okay, now that I have imported from VMD, it has just one atom type, okay, but further I want to define 5 atom types. So it's better to write here 5 atom types. Then we have the mass, then we have the simulation box. This is the size of the simulation box, so I just write . Okay. However, you know, this is well related to the X dimension, Y dimension, and Z dimension. It's actually fitted completely the upper and lower side of the nanotube. But since I want to do the tangent on it, on the atoms, so I increase these bonds in the Z direction so that if I
maybe it's instead of a 0 and X.
Oh, thank you, thank you. Thank you. Okay. And yes, so I increase the dimensions here. For example, from 0, I can say I want it to be minus e, and 20 to this part, it becomes 50. Okay. And then we have the masses. Here also, we don't have the masses here, so we have to import it. And it's already for 5 types. I'm not going to write it again. But let's see. No, we need a place here. And then we have the name atoms. Make it space here. Right, atoms. And then just like this, we have to follow the exact format. Okay, it's ready. Or I just wanted to show you, for the simulation, we use this one. This is.
The file, yeah,
Yes, yes, the file you have received, we use it exactly for the simulation. Okay, it's okay. Okay. Okay, if it's not finished, we are going to use the CNT.data. And for any case, we have to just, match the format. And then for the simulation settings, the length of the tube is about, I wrote 3 nanometers, so it's about 30 angstrom. Okay, and I want to just fix the lower part, and I want to move the upper parts. Okay, so it's quite simple to that case. Okay, again, I defined the 2 regions. One of them 3 angstrom, the other is from 27 angstrom to infinity, which becomes 27 angstrom. This is the 3 angstrom at the top, and 3 angstrom at the bottom. We define the middle atoms here, and here I set the middle atoms to 3. We define the boundary atoms, and I set them to 5. Here is just as an example to see how to use the command variable. It's also an important command. The command variable, this is the name here. This is also the name. It can perform on some groups, or it can perform some, this style can be different. It can be equal, it can be atom. When it's atom, it means to perform this simulation on each of the atoms, okay? So here, for example, it means that here I want to actually find the radius of all the atoms in the carbon nanotubes. Okay, I want to find this radius. Okay, so I do. I try to find the center of mass of these atoms first in the x and y direction, and then calculate the radius of each of them, the distance of each of them to the center of the mass, and then do an averaging between all of them. Okay, but just, the x and y direction to find the radius. So the variable, the name of the variable, perform it on each atom. They are some, we do not have such a thing for every command, but there are some functions that are already defined in LAMMPS. It is the one that creates the center of mass in the x direction. XDM, all x. You can search all of them, you can search the functions that are defined in the manual, and you will see all of them. And also it's the center of mass, but in the y direction, and it's x minus center of the mass, square 2, x minus the y minus the center of the mass, and then with the squares of them, we can find the radius of each of them to the center, okay? And this is another version, after you find it for all the atoms, then you use compute reduce command. This is again the name. It shows on which atoms you want to perform the computes. And it says that please do the averages on the array that we find for each of the atoms. Okay, so this is how you find the radius, or this is the name I myself have put on it. There are some parameters that are already defined for LAMMPS. For example, PE means for it means potential. You don't need to define them, but I just write it for more explanation. You can compute, and you can here use some words that are some, he call it thermo keywords that are already defined for us, for LAMMPS. Okay, and here I'll also define the forces that are applied on the upper side with this command, variable equal. This is the function that is already defined for LAMMPS. It is the force. It is the name of the group, the force on the upper group in the z direction. Okay, again, variable. The name of the variable is applied force lower. It is equal. It is the style of the variable. We are not going to change it. The force that is applied on the lower group in the z direction. Okay. Then we can also compute the pressure, and with the pressure, it also means the stress. Okay, because when I write compute, this is the name, pressure, and this is the temperature that I want to perform the. When you see this, it means that the current temperature of the system is not really important. But for example, when you ask it to compute this one, it produces two types of quantity. One, it produces the overall pressure. Okay, if you when you want to call this one, we use this C underline 3. It is how we recall it in other commands. Okay, if you call this, it gives you the magnitude of the pressure. But if you write this is the case for some comments. For example, 1, it means that with this one, it also produces a quantity, a scalar quantity, and also a vector. Okay, from 1 to 6, there are different coefficients of the stress. Sigma xx, sigma xy, sigma zz. Okay. Yes, it builds that. Let's bring this one. It's better. Okay, so compute pressure, name the group and the pressure. Okay, this is the form of the pressure that it computes. Okay, and this is it is the scalar type, and this is the tensor type that it computes for the pressure. If you want to say just the pressure, you just should name it. Okay, but if you want to use the other components, Px, Py, these are also defined for LAMMPS, but you can also say that I want the first, which is Xx. The first one is Xx, the second one is this, or the sixth one is this, okay? Okay, let's just get this one. Here we also have the thermostyles. In this case, we also perform a minimization on it. It is really necessary to perform a minimization to avoid high. And here we have used conjugate gradients minimization style. And then we adopt the velocity to all the atoms. Again, we have a fixed. It is the name of the fix. And here we have NVT. This is another ensemble in which we fix the temperature. Okay, and it has other arguments. The first one is the initial temperature. This is the final temperature. For our case, we want it to be in 10 Kelvin, so both of them are the same. And this is a parameter called T-damp. It actually, it somehow shows, do you remember that I say that, for example, in NVT, when we have nose hoover, we are extending our system with a heat bath. Okay, it is somehow related to this heat bath. If it's small, it says that you have to, for example, if it's 5, it means that every 5 time step, you should force it to be 10 Kelvin. It fluctuates, you know, when you say 10 Kelvin, it fluctuates around 10 Kelvin. But every 5 time step, it should be 10 Kelvin. If it's, for example, 10 or 100, it means every 100. If that value is small, we have a lot of fluctuations. But if it's so big, it takes too much time to collaborate. A good value for this is 100 times of the time step, for example. Okay, then we define the time step here. We define the thermostyle here. The thermostyle means when you write custom here, it means that you can customize whatever properties you want to get. And okay, again, we assign a velocity to the lower part to be 0 and another to be 5 angstrom per picosecond, according to the limits. And another way, you know, one way to get the data is to use the log file, and another way is to use the fixed average over time, fixed. Okay, it is so simple. I'm not going to explain all the lines anymore because it is so simple to this one. Okay, we have just changed the number of the atoms that we want to fix and we want to. Okay, just look at this one. This is the last one. This is the last thing that we wanted to give us. It is the step. Okay, elapse is the step from the last fix that we want to do. We wanted to give us the radius that we have calculated. And also, for example, the force applied on the upper ring and lower ring. Okay. This command also writes the data. So if you want to use sometimes, you know, it's fine to do some simulations in the middle of the simulation, just save the data because, you know, otherwise it's not saved. You save the data, okay, and then, for example, here you read the data again and start another simulation with the previous one. Okay. Now let's run this simulation. In the previous example, actually what we got was the configuration, the videos. But now I want to show you how you can get real data from it. And okay. And that's CMT and run. I reduced the number of runs just to, you know, have the. Okay, let's first see what is happening. I delete this one. You can also run it if you want. Okay. You don't need to do anything, just you know, now, yes, write this in that CNC tensor. And you know that you write, of course, you should write this. Then then press. Press it, okay? Leonard? Ariel? Okay. Then, okay, one way is to say file new molecule, browse, and then find your, that's XYZ. This is the one that we use because it creates the XYZ coordinates. This is the one that we use, and you say open. And a more lazy one is this. One I want to of course, you know, I have increased the velocity so much, so you could see something here. So this is not really a quasi-static deformation. Do you see that, you know?
The results?
Yes, it is the configuration.
No.
This one is it must be, of course, tension, but as I modified the script for torsion of CNT. Okay. But okay, this is the shape, but this is not always what we get from molecular dynamics. Okay. If you don't say anything, if you don't have such a command here, log, everything is stored in a log.lamps, and it's okay, you can use it. But if you have some complicated steps in your simulation, for example, here I had a minimization, then I had a relaxation, and then I had the, oh, it's 1 o'clock. And then I had the simulation itself. Sorry. If you want to just break the log into different parts so that you can then analyze it easier, you can say log dot anything, whatever you want to be the name of the log file, and then it starts in another file. Okay, so these parts that is related to tension, because you know also I have some parts related. This is the relaxation parts. I have some parts related to these. This is the minimization parts, but that's just written the file related to the tension in this log.cnt.tension that I have myself named. Okay, this is the data that we have get. To use the data, you can simply open an Excel file. From here, data, close data, from text. Log.cnt.tension, import, delimited, next, space, next, and finish, and okay. Then you know we have, of course, this is actually a neat file because it doesn't have so much thing written to it, so you can easily do it with manually. Sometimes, for example, I put something, some parameter here, for example, filter, named filter, so that then I filter it, and or you can use the MATLAB software. Or any other codes, just. And to the right. Okay. Okay. Just, you know, doing it manually. So now we have the step, the elapsed. You know, elapsed is nothing. It's just a step that is starts from 0 in every new command. And we have the radius that we have calculated here, temperature, pressure, and a lot of things. You can do some calculations in the LAMMPS software. We can do some of them here. Now I want you to, I want to drive myself. I will drive the tension, the stress strain curve to find the Young's modulus. So I use the elapsed one. My strain here. Plus the velocity of the deformation. What was the velocity? What was the velocity? That was here. V small linear, it's 5. Okay. It's 5 angstrom per picosecond, if I'm not right.
Yes.
Metal. The velocity is angstrom per picosecond. So angstrom per picosecond, and our time step is our time step is this. But the time is picosecond here. So it is 1 femtosecond. The initial length, you know, I'm using the velocity, how much time has passed to show the displacement, to show how much we have changed the length of the tube over its initial length that was 30 angstrom, believe me. Okay, so this is the strain. And now I also want to find the stress here. Okay, this is a really rough calculation. I just want you to have an idea about it. To find the stress, I use, let's do this. To find the stress, this is the stress that it has calculated. Okay, but the fact is that LAMMPS cannot calculate, for example, when it says the stress, it means the force divided by the area of the simulation box. Because, you know, the volume of the atoms are not clearly defined. We do not have. So it is actually divided by the area of the simulation box, but I do a trick here and say, okay, this is the volume of the simulation box, but it was 100 in 100 divided by the real area that we had. This is P over this radius. That is why I actually calculated the radius. Yeah. So we have the strain versus stress. Okay, and the Young's modulus is the slope. Okay, 2 for the slope, again roughly say at trend line. Display equation on chart. Yeah, that's good. Okay. This but it's a little lower than what I expected. One moment. Oh, I got the same one. Doesn't different. Let's see. Okay. This was the same. Oh. Was 100. Okay. So it is the value of the Young's modulus that we have found. And it's in actually gigapascal because I changed the gigapascal here, the value of the stress to gigapascal here. Here. It is the pressure is in bar in the metal unit, so we changed it to gigapascal here. Okay, I think it's finished now. Thank you so much for your attention. Do you have any question?
So the installation about droplets, uncertain droplets,
Rubber?
droplets.
Droplets, yes, yes.
Droplets.
Mm-hmm.
So I saw that they start with a box
Mm-hmm.
and then it becomes a spherical droplet.
Mm-hmm. I see.
It's the only way. You cannot just start with the spherical droplets in the unit or reasonably.
Droplets in the liquid form, yes.
Liquid rubber, yeah.
Liquid vapor. You know, it also depends, you know, but because I told you, for example, for the lattice structure, we have the spherical form. You saw that, for example, we can define a region for it, okay? But maybe that is really the right word to do, you know, start from a box. You know, you start from a box. Okay, let me also repeat the question. The question was that, for example, if you have a droplet, which is actually in a spherical shape, and it is not in a lattice, it doesn't have a lattice structure. Yeah, so that because you remember that for the region, we have also, for example, a spherical region shape, and we could directly use it for that. But it is, for example, for nanoparticles that are made of metallic or metallic oxides. Okay, but if the structure is really more complicated, it's also a good idea to, for example, start from a rectangular simulation, a block simulation box, or even the one that I told you that it can have some more faces, okay, that is nearer to the droplet, and then you can increase without, you know, mapping the atoms. You can increase the simulation box, okay, and then you do the relaxation so that it forms the droplets. You know, actually, I have done something like that in one in our papers that it has not been published yet, but it is something like this. Let me see if I can. Yes, for example, you could see here, not here. Okay, I do not have that shape. But for example, you know, it was, you know, it is all the same. It is the simulation box, and the simulation box was rectangular, but in this direction, not. But then I increased the dimensions of the simulation box in these two directions. But this direction is unchanged because I wanted it to be periodic. And then I did the relaxation, and the atom tends to be here cylindrical. Okay, so I didn't have any confinement to put the atoms in a cylindrical shape, but because it's, for example, in the droplets, this figure is because, you know, it naturally tends to become like this. So you let it to form its shape. Yes, you have to wait. Yes, you can sometimes, of course, you know, for example, for polymers, I needed to increase the temperature a little more to, you know, increase the movement of the, so that they allow to form the shape that they want. Okay, but of course you have to be careful it doesn't, you know, evaporate or.
the